Welcome to another episode of Robo Papers. Super happy today to have Li Yi joining us. He is one of the authors of this paper called R2S2, Unleashing Humanoid Reaching Potential via Real-World Ready Skills Space. Thank you so much for joining us, Li Yi. Maybe
Yeah,
as a
thank you
start,
for
if
having
you
me.
can introduce yourself, tell us a little bit about how you get into this space. That'd be great.
Okay, it's my great pleasure to be here to kind of share this kind of works with everyone. I'm Li Yi. I actually am now assistant professor from Tsinghua University in China, and yeah, I graduated from Stanford in 2019 with my PhD. Kind of my advisor is Leonidas Guibas, and then I joined Google for like roughly a year and a half, and as a research scientist working on 3D scene understanding. I kind of like joined Tsinghua in 2021, and since then, I'm working on embodied AI in general and 3D scene understanding. Recently, right, we have like a huge interest on humanoid robotics and humanoid robot learning. So yeah, that's why kind of this paper is one of the early try we had done in this field. Yeah, yeah, it's hopefully we can share more details later in this episode with everyone.
Okay, awesome. Yeah, okay, cool. So maybe as a start, if you can share screen and then you
Okay,
can just talk us through. Yeah.
share the paper first, maybe,
Yeah,
or yeah,
up to you. Yeah. Yeah, I guess you can maybe share the website and then just give an overview. What is R2S2?
yeah.
I think, yeah,
So
the visual. Yeah, okay, this is great.
okay, so basically, this is like a paper focusing on how to make the sim to real of humanoid robots happening well, okay, especially in the multitask learning or reinforcement learning setup. So traditionally, like using reinforcement learning to learn all these kind of humanoid skills is one of the good option to go, especially for locomotion. But now we know kind of the robots are not just designed for working anywhere. They are designed to really kind of complement humans' labor force, and so they should definitely have the operational space similar to a human being. So that's why I want to make sure this humanoid, they can reach the whole 3D space rather than just like working to any places. So, but this requires us to handle kind of a lot of different humanoid skills. For example, like locomotion, squat down, like leaning forward, reaching, grasping, and so on, using kind of reinforcement learning to learn all these kind of skills. A single framework could be possible in a simulation, but usually transfers very badly to the real world. So how to really make sure this multi-skill reinforcement learning can transfer to real? So that's basically the focus of this paper. As you can see now, this robots are basically showing some of the examples on this Unitree H1 robots here. In this example, they can do autonomous kind of point reaching to pick up a box from the ground, or they can kind of reach out to maybe grasp cups through some teleoperation systems. So yeah, basically all these kind of skills are now kind of transfers well to the real. So this is because we have built this kind of real world ready skill prior. Okay, so telling them how to really handle these skills, especially when it's trying to kind of do maybe squat down, locomotion, all these kind of things in the same kind of task, right? So do you want me to show more details about this kind of thing right now? Or maybe we can discuss that later.
Yeah, I mean, I guess you can maybe show some of these videos as well. Yeah.
So these are some of the demos. So this kind of, if you have this kind of whole body, whole space reaching skills, you can of course port these autonomous tasks through some hierarchical reinforcement learning design. So basically in this demo you see here, we have, okay, so in the previous few kind of videos, you basically have this kind of autonomous skills. The low level is some kind of real world ready skill we have already learned previously. And on the high level, we have like another kind of high level RL policy, which tries to select proper skills in order to accomplish a specific task. Here, you see it wants to touch a point on the ground. So this really unleashes the reaching potential so that the humanoid robots becomes more useful. So not just those autonomous policies, but here there are more examples for teleoperation examples. Let's see, yeah. So you see, in this situation, we kind of we kind of tie up the humanoid robots by using like a mocap system to kind of monitor the state of the robots and then sending out the commands for its end effector, right? Basically, what is the position where we want this end effector to reach. So this kind of teleoperation in these slides, you see all these kind of teleoperation examples. Oops, it's kind of like a circling. Yeah, but this teleoperation is another important feature for this framework because we do have this kind of low-level real-world ready skills. So you can teleop the whole system to collect data where the robots is kind of working. So this is something, one of the motivation we started to work on this problem because humanoid robots is quite different from robot arms or kind of wheel-based robots, where you do have very nice teleoperation systems, which helps you to collect those robot data for you to maybe learn like embody foundation model or some other kind of big transformers. However, for humanoid robots, controlling that kind of stably in the real world itself is a big challenge. So it comes into a chicken and egg problem. If you want to do teleoperation, you need to have a policy which allows the robots to work in the real world first. But that also requires maybe data. So that's why we think, okay, maybe RL can be a good data provider, allows the robots to explore different places in the environments and then transfers to the real. So once you have this kind of low-level policies, the robots can really do a lot of things. Then with a kind of human in the loop issuing those commands and high-level commands, especially those waypoints, to gradually guide the robots to reach some specific regions you have in mind. This allows us to really collect data where the robots becomes more useful. So once you got this kind of robot learning humanoid robots data, then yeah, there are more things you can do. Of course, learning autonomous policies, which can do allow these robots to do this kind of maybe tabletop cleaning or like object reaching and grasping. Yeah, that's another big motivation. Starting from that motivation, we work on this project, tries to build a very stabilized and low-level control for these humanoid robots. And then we can start to use this methods to collect data and training maybe autonomous policies. So here are more primitive skills. So this R2S2 itself is actually like a skill prior. So this skill prior means we want to make sure we can do sample robust skills from that space so that it supports the high level planning. So in order to generate this kind of skill space, the first thing is to really make sure individual skills can be done nicely. So here is one example like locomotion, right? You want to make the locomotion robust. This has been shown in a lot of places how to make sure these big robots can work well and robust to disturbance forces. So we found that if you learn these locomotion skills alone, you can introduce a lot of good constraints or regularizations. For example, the gate is one of the famous regularization people want to introduce when they are using reinforcement learning to learn these locomotion skills. But if you learn a multi-skill, a multitask reinforcement learning, then how to really kind of introduce good constraints in this setup itself becomes much more challenging. So that's why we decided to first learn individual skills and by introducing a lot of human priors. So here for locomotion, of course, gait is one of the famous and useful prior. So this is kind of body pose adjustment. In this body pose adjustment primitive skill, by including squat down, leaning forward, all these kind of skills you need to adjust your body pose so that you can have a large reaching space. So here, of course, you no longer have those gait as your regularization. You probably want to introduce some another set of regularizations, for example, symmetry. Right? So when they are doing this kind of body pose adjustment, a lot of the time, their kind of leg joints have symmetric nature. We want to encourage the pose of the legs, the joint works, all these kind of things. They're kind of symmetric. And this will also stabilize the whole training process and making sure you do have this very good and stabilized squat down, leaning forward skills. And all these kind of primitive skills and also like hand reaching. So hand reaching, this is a more easier primitive skill. Usually for the upper body, if you want to reach some specific spots, you can use some IK controller. That's not very complex. But with just this kind of primitive skills, it's not sufficient to really span this what we call real world reality skill space. So of course, one naive idea or interesting, one simple idea is to just like a sample from these primitive skills using another high level policy and tries to accomplish various of tasks, either autonomous or teleoperation based. Now the issue is how can these skills being kind of composed and coordinated? When composition, we mean there are maybe multiple skills going from locomotion to like body pose adjustment or from body pose adjustment to locomotion. So, like a long tasks, all these kind of primitive skills, they have this kind of temporal composition. On the another hand is the spatial coordination, right? You do have the upper body, you want it to reach anywhere, but you also have the lower body, you have to probably walk to some space or adjust the specific pose of the legs. So this kind of spatial coordination and the temporal composition, they are not really there from these primitive skills. If you just sample these primitive skills and naively compose or coordinate those together, you will find this will introduce another sim to real challenge. Since the goal is to make sure this sim to real can happen really well, so we have to address this challenge again. So this is basically something very key to this project, how to really ensemble those kind of primitive skills. So this ensembling does not mean just like putting them all together, but also tries to expand the skill space to incorporate the transitions, the coordinations, all those kind of things. So of course, when we are learning this kind of transitions and coordinations, you shouldn't kind of forget these primitive skills. So that's why we kind of combine reinforcement learning and imitation learning together here, with imitation learning, learning from all these primitive skills, serving as the teacher, and reinforcement learning tries to give feedback to the skill library so that when transition happens, when the upper body, lower body coordination happens, there won't be any artifacts and the skill still transfers to real. So yeah, this part probably I will later look at the paper and using the figure that shows better ideas. But due to that kind of skill prior, this sim to real basically becomes solvable. And another nice feature of this framework is it can easily extend to a different kind of include more skills. For example, like not just locomotion, not just scroll down, and maybe sometimes you want to have jumping or running, although we didn't do that at this moment, but this framework is kind of general to incorporate more skills. So yeah, so here are just like examples I already showed in the earlier demos. So these are all kind of autonomous policies where the lower level is the skill prior, while the higher level is another RL policy selects the proper skills to do all these kind of things. And we kind of also support teleoperation as I just shown. So we do allow, so we do ask the robots to maybe use some of the human tools like and also we want to show it has a huge reaching space. So that's why we have this kind of scroll down, reaching objects on the ground and like a really standing up very high. So you see here, the knees is becoming a pretty kind of not very bended anymore. So previously, to allow a stable locomotion, usually the robots needs to kind of bend its knees a little bit. But now, if you really want to reach a high space, you need to kind of stand up. At this moment, keeping balance is also a challenge because, yeah, you need to better kind of pose your center of mass and so on. Yeah, you can also use these kind of tools to write some of the characters here. And yeah, this not just happens on the humanoid H1 robots, but also on the smaller and easier controlled G1 robots. So yeah, this teleoperation is basically something pretty important for this project. From this figure, I think it's probably better for me to explain the key, which is how the skill ensemble. By the way, if you have any questions, just interrupt me at any moment. Yeah, I'm probably like just talking on my own. Yeah. Okay. So yeah, for this figure, I think
No,
is
these are all like really incredible. Oh, no, I was gonna say like, yeah, I just want to say like the demos are incredible. I mean, Chris and I have seen a lot of incredible demos on this podcast, but I think yours is some of the more impressive ones, certainly for whole body humanoid. But yeah, I was gonna ask about this diagram, so it's perfect. Yeah, so maybe you can
yeah,
talk us
I
through
will
how you
provide
set
a
up the
little bit more
whole.
information. Yeah, so this is basically shows how this kind of things happens really from maybe like a way CS and robotics people feels more intuitive. So here, this is the whole pipeline. We kind of divide that into 3 blocks. So on the left is the primitive skill learning, which I already kind of introduced to some degree. So we want to kind of incorporate different primitive skills necessary for this whole body, whole space reaching thing. So specifically in this project, we consider 3 primitive skills. One is locomotion, basically navigate to any position. So here you will have the velocity and also whether you want to kind of rotate yourself to like your left or your right. And for body pose adjustment, so this is kind of yeah, some another key feature here. You want to be able to like squat down, leaning forward. So here we find firstly at the very beginning we think okay, changing our height is one of the important thing, but we find it's very important to kind of disentangle the pitch kind of command describing how you're really leaning forward. So we found one example that if you really want to reach something far away from you on top of a table, then you don't need to kind of squat down, but you need to lean forward to reach your hands. All this kind of thing is important. So if you just mix all these kind of things together, single squat down policy, then you won't be able to control all these degree of freedoms to accomplish this kind of complex tasks. And yeah, that's why for this kind of body reaching, you will also have different commands controlling the height of the robots, the pitch angle of the torso. And for hand reaching, you will have basically the end effector place position telling you where you want this hand to go. Okay, so all these primitive skills are the basics, but as I just mentioned, they're not enough, they're not sufficient, especially when transition and spatial composition happens. For example, we find that when you are kind of walking to some place and then squat down and grab object from the ground, if you directly kind of sample these skills, the robots tends to becomes kind of trembling, right? Because it cannot really find like a proper position to transition. It cannot find a proper pose to transition from the locomotion to the body pose adjustment. Maybe you send the command when the feet is still on the sky. At this moment, then the robot will becomes kind of out of distribution because it never seen all these kind of states during training the body pose adjustment primitive skills. So all this kind of composition is a big issue. So traditionally, I was working in the character animation domain. In that domain, people don't find that to be a big issue. If you have different skills, you just like embed it into some space and then you sample from there. And the robots just like, sorry, the character just like transitions naturally. But now it's in the real world. We cannot tolerate any artifacts and any instability. So that's why the key thing is the skill assembling. How you can make sure all these kind of skills are properly used to form a good and nice skill prior. So here, one simple thing is to use imitation learning. So you just train some student policy, which imitate all these kind of primitive skills. And especially if you don't want to forget all these kind of primitive skills, but just like doing imitation learning, like trying to kind of distill all these kind of skills into a single space is not sufficient. It won't really create transitions. So that's why we have to also on purposely kind of set up like a environments, issuing all these kind of transition commands and composition commands to the robots to kind of challenge the robots to see whether artifacts will happen. So once we set up this environment, we send all these transition commands, composition commands to the robots. And now the imitation learning is no longer sufficient. So we will introduce another reinforcement learning branch, tries to, through trial and error, providing this kind of feedbacks from the environment. So that's why you see in the middle block, there is a dagger and there is a PBO coming from two directions. So this skill, this skill space is actually something in the middle, and we learn a student policy which can help us to inherit all these primitive skills, but also handling those transitions and compositions. On one hand, the student policy will learn from the teacher. This is why it's called student policy. On the other hand, there will be some sort of like a word provided to the student policy, especially when transition and composition happens. Although this lines is a bit complex, but you can see here when the goal is given to the student, this goal could be reaching at some specific spot, or doing locomotion first and then scroll down, or kind of scroll down, stand up and then navigate to some place. So this goal could be this kind of transition and compositional commands, and these commands are given to the student policy. When the command belongs to some specific skills, the teacher policy will be activated. The student can learn from those teacher policy. So when the commands incorporate some transitions, so the reinforcement learning on the lower half will basically provide some feedbacks from rewards to the student policy. So that's basically how this thing works. And the student policy itself is kind of designed using a conditional variation autoencoder. So this tries to model everything in a latent skill space rather than in a primary skill space. So although we don't really, in generally speaking, we don't really feel this latent space or kind of explicit kind of primitive skill space are not that different. But here we learn this latent skill space more for unifying the commands. So because for the primitive skills, they have different commands, some controlling the lower body, some controlling the upper body, and sometimes like the horizontal velocity, sometimes the vertical height and pitch angles, all those things. They're pretty heterogeneous commands, making selecting those primitive skills, issuing those commands not convenient. And so one simple thing is just to unify all these kind of things in a latent skill space and using a unified command interface. For example, we have a super long commands with all these kind of things being provided. And if some commands are not given, they're just like some blank symbols. So with a unified command interface and also a latent skill space, you can now more easily kind of support downstream tasks, which needs to select proper skills from this skill prior. So this is basically how this skill assembling process works. Once the skill assembly done, I think the most important key thing of this work has already been finished. The next is about applications, where you can now maybe sample from this skill space to accomplish some high-level tasks. Here we consider some of them like point reaching, like box pickup. So because all these kind of tasks, they can be characterized as like a robot touching a sequence of the points. So for example, for box pickup, the robots can first touch the two sides of the box, and then maybe lifting is moving the hand to some upper kind of position. And for point touch, you can issue a single point goal, but all a multiple kind of sequence of point goals. These are all possible. So this kind of task information they're given to a high-level policy. So the high-level policy basically plans in the latent skill space, and it well, just like can output a latent action, which can be decoded into the real kind of robot control actions. So of course, this high-level policy can also be learned using reinforcement learning with some of the task reward being provided to this whole policy. Yeah, I think this part is already standard. So, but the nice thing is not only for like high-level autonomous policy learning, but you can also easily support those tele operation as I just mentioned at the very beginning. So you can just do this point reaching just by kind of using maybe a VR system to kind of synchronize or monitor how the human is moving their hands, and then just issue this hand and effective position to the robots. And the robots is now able to kind of reaching that specific spots in an online manner. So this is basically how the teleoperation happens. So
Yes.
for this teleoperation, we also have like a video originally I shared on the Twitter. Maybe I can find that video too. I'm not sure. Yeah, that video is not in this page. But yeah, I think that paper is also interesting, showcasing how this kind of skills can be really used in this teleoperation system, helping us to collect data, boosting the amount of humanoids data for maybe later large models or humanoid skill learnings. Yeah, so maybe I can talk about that later. Before I really move on,
Uh,
I probably pause here a little bit for any kind of questions or interactions we might want to have. So once
yep.
you get this kind of like latent skill space, so because it has all the primitive skills and all the transitions, and also they are already kind of verified to be sim-to-real transferable. So this is another good advantage. So before you learn, before you kind of like ensemble all these primitive skills, you can do sim-to-real verification to see where the artifacts come from, how you should change and adjust your rewards, and even using real-world data to improve the sim-to-real transferability. So these are all possible for a single skill learning and also very easy for single skill learning. So once you have all this kind of sim-to-real transferable primitive skills, you just ensemble all those things and with the proper transitions in the latent space. So this allows and also the transitions due to the good post priors from those kind of primitive skills and also the reinforcement learning reward. We find it can transfers to real very nicely in this situation. So all this kind of thing allows us to now learn some autonomous tasks, for example, through a hierarchical RL paradigm. Here we can consider a lot of tasks. We found a lot of like reaching tasks can be considered as touching and reaching a sequence of points. So that's why specifically in this project, we consider point touch and box pickup as some of the candidate tasks. So we can basically training a high-level RL policy which outputs some latent action. These latent actions will be decoded into the real robot actions to control the robot torques. So this high-level policy is also trained through trial and error in the simulator with only some simple task-related rewards. So because the skills are now kind of transfers well to the real, so you can simplify the high-level policy learning dramatically, easily achieve all those kind of autonomous tasks I just shown previously. So yeah, so I think this is, but this is not the only good thing. The other good thing is you can also do teleoperation, as I mentioned at the very beginning, right? So teleoperation itself is important for humanoid robots and these skills because they're now real world ready. So even though when user is kind of sending conflicting or kind of like quickly transitioning commands, the system can still kind of performs reasonably well. So this allows us to maybe collect data where the robot is touching the ground, grasping objects on the ground, or reaching some high spaces, and allows us to maybe later training even higher, even larger scale policies to facilitate the embodied AI learning. So yeah, that's
Uh,
basically how this framework goes. I will pause here.
yeah, I have a question about the teleoperation. So
Mhm.
during teleoperation, which policy is running in real time? Is it the student policy in the skill assembling step?
Yes. So for the high-level policy, the skill assembling thing is the only thing. We don't have the high-level policy anymore.
And
Yeah.
so the teleoperator is probably giving kind of n effector like target, and
Yes.
then
So
I
you
see.
have different
Okay.
design choices. In our specific implementation, kind of we developed a teleoperation system called Open Whole Body Teleoperation. Also, kind of
Mm,
shared a video on my Twitter. So in that teleoperation system, we basically use a pair of like a VR headset to kind of support the whole teleoperation system. So you have
mm,
the VR headset. The VR headset will just monitor how the user's hands is moving. So this end effector position is one of the teleoperation commands sent into the system. Apart from that, we'll also incorporate a pair of remote controllers. So this controllers, we have several buttons on that controller. You can press different buttons to control the lower body skills, for example, like walking forward, walking backwards, or if you want to scroll down, there is some specific buttons. If you want to leaning forward, there's also like a button allows you to continuously adjust all those kind of bending angles and squatting heights. So this lower body thing is mainly controlled through these buttons on the controller, while the upper body, especially the hand and effector position, is read out from the VR headset. We found this tends to be more kind of stable compared with directly using the VR for whole body control. And so you can also consider using VR to read out some of the end effector position in the work coordinate system, and then tries to use that to estimate the heights, the body pose, and all those type of things are pretty standard in the VR community. But we found that thing to be pretty not quite stable, especially if you want this to work in a real kind of system to collecting data. You cannot really tolerate the robots to fall down very quickly when you maybe collecting one kind of trial. So if you really want to prioritize stability, you will sacrifice some of the flexibility and some of the kind of interface simplicity. So that's why we found introducing a pair of remote controller to control the lower body. It on one hand allows users to better specify their own needs. On the other hand, it's also quite stable because the user can control the commands and using issue commands following our instructions. And for example, if you just like send the commands to let the robots to local mode, for example, if you have a VR headset and people are kind of squatting and working at the same time, because now this skill is not in the primitive skill library, the policy will probably fail, right? But if you use the remote controller, user can be instructed to maybe walking and locomotion. They should not happen at the same time. They can transit. They can have a nice temporal composition, but you shouldn't really expect the robots to squat down and walking at the same time. So yeah, that's also another reason for us to design that kind of teleoperation interface.
Okay.
Mhm. Yeah.
Cool.
Yeah, I think for the teleoperation video, yeah, I'm not sure whether I have that one because this is a teleoperations video, like a teleoperation project. We kind of collaborated with Galbao, the startup in China. So maybe I can just like show some of the teleoperation systems feature, so for the audience to get a better sense why we think this is like a good thing. This video, yeah, from here maybe. It shows first the motivation of using this whole body teleoperation rather than just like the tabletop teleoperation. Previously,
Mhm.
like Unitree, UC San Diego, they already kind of open source some of the tabletop teleoperation frameworks, but with only kind of this like standing and walking thing is not sufficient to really match humans' walking space. So that's why we want to develop this system to leverage the previous skills we learned to support the robots. So this like teleoperating system has three key features. I would say I will pause here a little bit. So cross robots means this teleoperating system not only supports Unitree H1, we can also use the same skills in Unitree G1 because we started with Unitree H1, although I know that's no longer very popular these days. Because we started from Unitree
Yeah.
H1 and we actually found its control is more challenging than Unitree G1 because it has
Mm.
taller heights and squat down and bending, all this kind of thing. If you want H1 to really touch the ground, its control is much more complex. Using
Mm.
G1, we quickly set it up, but using G1, H1, it really spent a lot of efforts to making it really works well in the real world. So that's why we want to highlight this feature. So this methodology is can be shared across different robot types. And for quick deployment, we are if referring to the VR system, because we know there are also kind of different ways to teleoperation, maybe through isoskeleton. All those things are very nice. But one thing is they require more hardware setups. We originally started this project by ordering some of the hardware to tries to build a isoskeleton-based teleoperation system. So one of the intern students spends like 2 months and didn't really get it to work. So that's why we kind of gave up. So we think, okay, we really need something which can be easily set up even for beginners. So that's why we decided to choose this VR-based teleoperation system. And for sim and real, it means now the system not only works in simulation, but also in not only works in the real world, but also works in simulation. So we do develop some of the features also in different simulation platforms. For example, in Majorcal and also in ISAC lab. So for teleoperation simulation, because we know there is a branch of work from NVIDIA, they are really kind of using this simulation environments to augment the teleoperation data, right? So we think this is like very good thing and we should keep that feature. So if you can also do this whole body teleoperation in the simulator, then you can easily randomize the environments, randomize the kind of the trajectories and to augment the data to make sure you have much more data. In the end, it's a combination of the sim data and the real data for learning downstream humanoid foundation models. So these are the three key features for this open whole body teleoperation system. Yeah, so now you see we can just like the robots to maybe scroll down, fetch up something and handing it over to the others. So this is showcasing with a VR headset. It's pretty easy together with a pair of home body controllers. You can do this teleoperation in both indoor and outdoor environments. So here, yeah, so the robots is pretty robust to different terrains. The carpet is pretty soft. It's okay. The outside kind of terrains, it's quite different, but still like okay for the robots to doing this kind of squat down motion to the ground. Yeah, we really want to showcase. Yeah, this is about like a teleoperation in the simulator. We don't have much kind of resource in this video, but maybe later this month or next month, we will also kind of deliver some demo videos showcasing how users can use this teleoperation largely in simulation to collect data. So this, yeah, this only requires some tap top and VR headset. You can already do all these kind of things. Yeah, I think this is basically this year there are several works targeting on this topic. I would say this work is one of the thing which pretty robust on its own. So I would recommend anyone want to use this thing to collect data, you can probably try it out. It's all open sourced. Yeah, this is about how the teleoperation system really works. Maybe it better answers your. So the high level policy is just for autonomous policy, but for teleoperation, it don't really require the high level RL anymore. What you do is just to track all these commands and also with the robot states, you just use this kind of latent skills to kind of decode the action. So now you are kind of directly sampling the skills from this skill prior to tally up the robots in a real life.
Like yeah, I know about this open WBT. Yeah, I'm
Uh-huh.
glad you get to talk about this as well, and thanks for open sourcing this. This will be very helpful, I think, for the
Yeah, we
community.
do get some of the feedbacks from the user nowadays. They're also helping us together to improve this teleoperation system, and also we keep working on that system. We know now in this system we emphasize a lot on the stability, so we don't really allow the robots to really work like a human or copy paste humans arbitrary motion. I know that is fancy, but probably that's not the first step for a teleoperation system to stably working for a long time. So we can now do, we also kind of started to use this system to collect data ourselves. So we can use this system to collect data for hours without kind of robot kind of falling down, all those type of things to happens. So I do think this is like a very nice way for everyone to really get into this field. Yeah. And let's see. Okay, yeah, this is about the Unitary H1 thing. So we found, okay, H1 is no longer very popular, so we just like put it in the end. But I have to say, this is really more challenging than the Unitary G1 thing. And also, this is the only robots now compared with G1, which can match humans' working range, right? If you want, we know the G1 is just like 1.3 meter. You cannot really expect it to reach like a 2 meter high position. But with this H1, you can always do that. This is to showcasing, yeah, we can match like
Yeah.
an adult's working space, kind of like that.
Can I ask you a question about the one on the extreme right, right, where the robot is kind of bending forward to reach
Yes.
for the cup? I think.
Uh-huh.
So this is teleoperation, right? So
Yes.
what is a teleoperator doing? The teleoperator is basically saying stay put, stand at the same position, but then he's pushing his like controller forward. Is that what will induce the robot
Yeah,
to
I
stretch
think
out?
this is a very good question and also highlights one of the important feature I just mentioned earlier. We have to kind of decouple the height change commands and the kind of torso angle bending commands. So you have to like make sure you do have these degrees of freedom separate. Otherwise, when you are kind of like bending forward, you squat down. When you squat and bending forward, this is not something you want. So in this teleoperation case, the users will just use the hand to issue the commands that the robot should like moving its hand forward. While the for the body pose, it will not allow the robots to squat down, but only changing the pitch angles. So that's why the robot can just stand there and bending forward and to touch the robots, touch the objects. But I have to mention this is also challenging for the robots. If you don't allow it, sometimes you see demos on the internet, people have these robots always bending and kind of like squatting at the same time. So because when it tries to bending forward, the center of the mass shifts dramatically. If you do not really adjust your kind of like a leg pose, it might encounter instability. So that's why we also kind of carefully tune these skills, these primitive skills, to make sure it can just stand there and bending forward. Even when the center of the mass shift forward, it can still be stabilized there. So if you learn all the skills together with a multi task RL framework, I would imagine this is very hard to achieve. But now, since all the primitive skills are kind of engineered and carefully tuned to incorporate those regularizations and solve the real world kind of artifacts, then you do support this thing.
Yeah, that's awesome. Yeah, do you have more videos to show about this Open WPT?
I think yeah, this is some interesting thing like showcasing we like the robots to route some characters. Yeah, I probably don't have more.
Oh, so actually, I have a question about that calligraphy thing.
Yeah.
Can I ask, like, so I like the robot is bending down while he's also moving the hand. So this is teleoperation, right? So what is the teleoperator doing? Is the teleoperator telling the robot to start slowly squatting down while he's using his hand to do
Yes,
to
yes.
write? I
So
see.
this also challenges the teleoperators a little bit because you need to care more things, not just how your hands moving, but also how the lower body moving. So the teleoperator needs to issue commands to the any factor and also the lower body, the height of the robots to maybe instruct the robots to kind of squat down a little bit to adjust its body pose. So
Probably through a joystick or something. Okay.
yes, yeah. At
Mhm.
very beginning, this is not that intuitive, but after several trials, the teleoperators can get used to that.
Yeah, humans are very flexible. Yeah, yeah, that's awesome. Yeah, if you could maybe go back to the diagram, I think maybe me and Chris have yeah, quite questions about that. So maybe as a first one on the step one, I'm curious, like, were there other primitive skill that you guys also consider besides, like, before nailing down these three?
At the very beginning, we kind of like considers all the popular skills people are interested in, like for example, jumping, running, those type of things. Because previously, when people are talking about humanoid locomotion, especially multi-skill humanoid locomotion, they kind of consider all those type of things. But we find, okay, on the first hand, it's probably not necessary for the robots to really reach all the positions in the whole 3D space. And secondly, like just introducing all those skills means more kind of trial and errors and engineers tunings for the primitive skills. We started from the H1 robots, right? So letting the H1 robots to do the locomotion, body pose adjustment, all those type of things stably well is already pretty time consuming. And we don't really want to spend more time there to just like incorporate a little bit more skills. So that's why we decided to finish the whole pipeline first and just leave more skills to future works.
Yeah. So I
I,
guess so from yeah, yeah, Chris. Yep.
I had a couple more on this. So like, you have these three primitive skills. So you showed a bunch of things like the like carrying two-handed boxes and so on. So like your hand reaching skill isn't that just like one hand reaching is enough to train all of those different things. You don't need any particular, I don't know, way of learning constraints between the two
Yeah, yeah.
hands. Or
For hand
yeah.
reaching, it's not just like a single hand. It's pretty easy to
Oh, okay.
support multiple hands because now it's
Hmm.
just like some IK based control. So you just like issue multiple commands and
Yeah, makes
solve
sense.
the IK for each individual hands like arm separately. Yeah.
Yeah. Okay. Cool. Yeah. So I guess what is the role of the I know you explained this earlier, but like, why do you need the PPO so much? Like, what is the objective of the PPO? Is it not like, is it training? It's the joint task reward, right? So it's all of the different tasks together. Okay, all right, then,
So,
yeah,
so
gotcha.
for this PPO, it will incorporate kind of different rewards. For example, it will have the teacher specific rewards. For example, if it's doing locomotion,
Yeah,
now you will of course have the teacher policy, but also you will have the rewards inherited from all those kind of teacher policies. But also you will have some general rewards. For example, preventing the robots from falling down, preventing some kind of action kind of disturbance. You will try to encourage the action to be smooth and also the states to be smooth so that you don't have like all those kind of artifacts. So these general rewards are also one part of this PPO. So the role of this PPO is to just to make sure when transition happens or when upper
right.
and lower body composition happens. For example, when you're moving your hands, you shouldn't really kind of the lower body should still be stable. And when you are kind of
Yeah.
like a maybe walk to somewhere and scroll down, then this transition shouldn't run into artifacts. All this kind of transition based thing is the key for this kind of PPO thing. Yeah, they provide a reward so
Cool.
that you don't really have those artifacts and you don't really fall down when transition
Yeah,
happens.
no, that's very cool. I guess I'm what I'm surprised by is that so like I guess the clarifying question and then what I'm surprised by. The clarifying question is that like so like are just taking the reward. So like if I'm transitioning from like locomotion to hand reaching or something like that,
Yes.
then I am just adding in both of the reward terms for those two subtasks into your PPO, or is there something more, or is there something different going on?
Also, there is actually some indicator functions depends on
Okay,
like the commands. So maybe the commands is from locomotion to body pose adjustment.
I see.
When the command transits, the reward will also kind of like change to some degree. So the reward is a
Okay.
command dependent reward, basically.
Okay, so it's just doing one of them at a time, or it's just whatever whatever command or commands are actively being received.
Yes,
I guess.
yes,
Okay, that
yes.
makes sense. But then, so you don't, do you need to like co-tune these, I guess is the next question. So like, you were, I think part of the appeal, I guess, of the primitive library is that you can design all these things independently. Do you need to like co-tune them to make sure that like the reaching term doesn't like overwhelm the body pose adjustment term or something like that? Or does that question
Yes.
make sense? Okay.
Yeah, yes,
Yes.
yes, of course. So that
Okay.
is
Yeah.
also why this skill assembling is important. So for
Yeah.
like maybe hand reaching, we are training locomotion, don't consider hand reaching. But now when the hand is really moving in the whole space, because especially when you're grasping object, there is also the center of mass shifting somehow. So it's not just like locomotion alone, it's sufficient. So that's why
Right.
in this kind of like it's not just about, it's also about composition of like a spatial
Okay.
composition, spatial coordination. You need to kind of spatially compose the upper body and lower body together. So in this case, the reinforcement learning will have the rewards for the upper body and the lower body. Oh, so sorry. For the upper body, it's just RL. It's just like a IK based thing. But for the lower body, now the reward needs to basically handle more things. It need to be keep balanced when the upper body is moving. So
Yeah.
this is kind of I wouldn't say this is like a co-tuning because the hand reaching thing itself is not just like it's not an RL policy, but it do add kind of disturbance to the locomotion policy. You have to now
Yeah.
tune your locomotion policy so that it's more kind of robust to the upper body movement, and also for the body pose adjustment, it's the same.
Right. Okay. That makes sense. Yeah. So you don't, so this is probably because I guess maybe part of what was confusing me there was like if you wanted your RL policy to like reach a particular position or something like that for hand reaching, and I guess I don't know how the rewards are structured, but if you wanted to reach a particular position, then obviously the body pose or locomotion would strongly impact its ability to reach any SE3 position in
Yes, yes,
space, right? So
exactly.
then those would fight each other. But okay, that explanation makes
Yeah,
sense.
actually,
Sorry.
we do think
Yeah.
about like using RL to do the hand reaching at the very beginning, but we found that's actually complex things. And
Okay.
especially you
Yeah.
just mentioned, yeah, when the lower body is moving, then it will just influence the hand reaching kind of accuracy. And now you have like a two RL which depends on each other. The upper body
Yeah.
RL will super sensitive. So that's why we just use the IK thing. Yeah, that's sufficient for the hand to reach any space you want.
Okay. Yeah. Makes sense. Cool.
Yeah.
Okay, so another question on this front. So like I am curious about how sensitive all this stuff is. So like by which I mean like how long did it take to train? How long did it take for you to set up all these rewards? Because you also have the dagger versus PPO trade-off. I say where you like start out with more dagger, right? And eventually
Yes,
it's all PPO. Yeah, okay.
yes, yes.
So like
So
yeah.
at the very beginning, it's all dagger, but it's not. It's never all PPO. I have to say.
Oh yeah. Okay, right.
At the very beginning, it's mainly dagger, and later it gradually goes to dagger plus PPO. It's never all PPO because we don't want the student policy to forget all those kind of teacher policy skills.
But don't you have the teacher rewards still? Why do you need to preserve that little dagger slip?
Yeah, we do have the teacher like rewards, but now because the transition happens, the skill is more kind of like you have multiple kind of skills learning all at the same time. They are kind of
I see.
sharing the network weights, all those type of things.
So it's to
So
avoid forgetting? Is that the
yeah,
okay,
it's
okay,
possible
okay,
for
cool.
skills
Makes
to
sense.
influence each other. That's why we do still
Yeah.
enforce the dagger to play a small role to
Okay, cool.
prevent from forgetting. Yeah,
Yeah, makes sense. All right.
yeah.
Yeah, I'm curious. So when you finally start doing all these sim to real experiments, I know you have some charts that kind of show against baseline. Do you want to talk us through some of that and how do you actually evaluate?
Yeah, that's a good question. Yeah, so these are just like showcasing the reaching space of the robots. It's really matching humans' reaching space. Yeah, we do have some experiments trying to compare our method with baselines and also the ablations of our own methods. So here, yeah, on the first hand, we tries to compare the reachable space of different kind of policies. So we find, okay, so the reaching space is indeed different, especially if you want the robots to kind of touch the ground and reaching very high positions. So the reaching space itself is one of the evaluation metric. So whether you can reach all these kind of positions in the 3D space reliably, well, and we find that if you consider this sim evaluation and real evaluation, right? So this is easy. You can just do that in the simulator. But for the real evaluation, now we find with different skills being removed, this p, they are basically referring to the height, the pitch angle. So they are all important for the body pose adjustment, so that the robots can have a pretty huge reach space. So if you remove any of them, the reaching space will be dramatically will dramatically vanish to a small region. That is about the reaching space evaluation, showcasing this work to have pretty good reaching space and all the commands that are important. So this is about the comparison with different RL learning paradigms. So this is actually done in the simulator because evaluation in the real world is pretty expensive. So we started to do all this evaluation in the simulation environments. You will find the vanilla PPO without any all this kind of hierarchical sophisticated. So we're just using the autonomous policies to do this evaluation. It will include the success rate and also the distance error. So for the distance error, it refers to how far your NA factor is reaching is from a specific target points, and the success rates, as long as the NA factor is close to the goal position within a certain distance threshold, we'll just treat that as success. So these are two metrics we use to evaluate this kind of reaching tasks. So the point reaching, the point touch, and the box pickup, they both have their own kind of set of evaluations. So we compare with the very vanilla PPO, which is pretty bad in all different cases. And we also do ablation. So these two features, one is the latent skill thing, the other is the skill ensembling thing. So if you remove the skill assembly thing from our method, you will find it's no longer working very well. This is due to the transition and composition things. Those are pretty important. And the latent skill thing is a way to unify the command space so that you can easily sample from a more homogeneous skill space rather than the very heterogeneous primitive skill library. So we found that in practice also improves the performance a lot. Without that thing, you can also design a high-level policy to select one type of primitive skills or like a directly select from the skill library, all those type of thing is not as good as using a latent skill space to model all the skills. So yeah, this is a bit ablation study. So this is also showcasing whether sim to real is okay. So when the cross happens means we tried, but we find it easily failed and even hurts the hardware. So we cannot really afford doing any real to a sim to real thing. And for this thing, for the third role, sometimes it can work to some degree in the real world, but it trembles, it has artifacts, and when the transition happens, instability happens. So although we say, okay, this is sim to real transferable, but it still has its own artifacts.
Yep. Sorry. So distance error. So is what you're doing in? Are you putting some kind of mocap onto the physical robot and then get the distance and then the delta between that and what is the difference you're comparing for distance error?
Yes. For distance error, if you do that in the simulator, it's easy, right? But if you want to do that in the real world, you do need a mocap system to help you to measure the kind of any factor position precisely so that you know whether it matches the goal. So that is exactly what we are doing. Yeah, we have the mocap marker. If you examine the early videos, you will find there are a lot of mocap markers on the H1 robots. So that is mainly for teleoperation and for evaluation.
Cool. I see.
So why do you think that the latent space did the latent space help with sim to real, or is it, or why did, if so, why? I guess, or is
Well,
it
it
just
clearly
that
works because without latent
yeah,
space, it's definitely half as good. Only
yeah.
right.
Well, why?
Yeah.
Why then? I guess why does the latent space help with this?
Yeah, I think for latent space, it's easy. It's easy to kind of incorporate all this kind of transition thing, and also because for transition, you can also
Yeah.
treat that as a separate skill, right? If you treat that as a separate skill, then that's easy for the high level policy or the teleoperation system to just like sample those things to make sure it can nicely and stably transition. If you do not use the latent space, then for the original command space, then there won't be like a skill corresponding to those transitions. So that's one of our kind of intuition for designing that latent space.
So it's really so it's like the PPO component really is what's like being able to learn all those transitions and capture them
Yes.
in a single latent space that does it. Okay,
Yes,
that makes a lot of
exactly.
sense. Cool.
Exactly.
Awesome. Yeah, very cool.
Yeah. So
Yeah.
I guess what would be an extension of this work? You mentioned earlier you probably want to add more primitive skill,
Yes.
maybe over time.
Uh-huh.
Like what would be the next one or two that you think would be quite useful to start adding on to this repertoire of primitive skill?
Yeah. I think adding primitive skills is definitely one possible way to extend this work. For example,
Mhm.
allowing the robots, for example, climbing stairs, right? So that will make the teleoperation system more useful for the complex environments, complex terrains. But yeah, at this moment, we think like making this teleoperation system more flexible is also something pretty important. Right now, the stability is the key. But since we already get the stability, the next thing is can you make it more flexible to maybe also using the lower body, have a more control on the lower body to maybe use the lower body to manipulate objects sometimes. Right? For example, kicking football, all those type of things. With only upper body, you cannot really do that. Maybe I know like Jiajun Ziyuan, they recently have works related to that topic, but how to really have a good trade-off between the stability and the flexibility. I think, yeah, that's one key thing we should consider when you are keeping building this this whole body teleoperation system, and also how to incorporate vision. So at this moment, we know on the bottom of this teleoperation system is some robot autonomy, right? So it's not like a pure human-controlled teleoperation. It's some shared autonomy with certain autonomous skills from the robots and certain kind of commands from the humans. So how to increase the autonomous capability of the robots, for example, by including the vision, so that now the robots can do more fancier kind of stuff without being to specify every joint's commands. So this is also one of the interesting things we are considering and actively working on. And of course, supporting different teleoperation kind of forms, for example, isoskeleton or even like just only like a VR exoskeleton or even just like a web camera. How can we really make the teleoperation system cheaper and more easier to be set up? This is also something pretty interesting. Yeah.
That's awesome, man. I'm curious though, like, as these things go down, how much value add will you get from human basically jumping through all this like UX, let's say deficiency of teleoperation? Like how much can you gain from human teleoperated humanoid
Yeah.
versus just let's say learning from video, like YouTube, like watch Lionel Messi play and then just have it like just do it that way. What sense?
Yeah, so you're asking like, what's the value of have a human teleoperator? Why not just like learning from human videos, right?
Yeah, yeah. I'm curious what's your take on that, because it's a lot of effort,
I know, I know. I
to
think
force
learning
a
from
human
video
to.
I think
Mhm.
learning from video is a very kind of promising direction. Myself is also kind of heavily investigating on that topic. For example, how to extract human motion examples and using that motion as a template to do retargeting. Specifically for dexterous hands, for dexterous manipulation, we have several works like transferring humans' motion skills to like a robot dexterous hands and to do dexterous manipulation. I do think that's like a very kind of interesting thing to pursue from a academic perspective. But I would say that sometimes we just assume the internet data is endless. Most of the time we find it's not really the case, especially if you care about the data quality. So video is everywhere, but high quality data is not everywhere. So if in the end you want to focus on get high quality data to solve your specific task, then whether that data comes from video, from some teleoperation, or it comes from like a unpurposely collected video. It's all possible, right? You might probably want to collect videos on your own to get some more video data, and then it's not that different from teleoperation anymore, unless that is cheaper, maybe. Yeah. But I wouldn't say the high quality data is already everywhere on the internet. Even if it's there, getting all those data itself is a super challenging thing. So that's why I think teleoperation, at least to some degree, still has its own value. But it's not just like using teleoperation to solve everything. Now, that's why we're keeping increasing the autonomous capability of the humanoids through reinforcement learning, through trial and error. So when you are learning all these kind of things, basic skills from the simulation environments, the rest, high-level task learning itself becomes no longer that challenging. With several samples, you can probably already know how to do planning, especially nowadays with LLM, VLM, all this kind of foundation models development. It's pretty foreseeable. You can leverage those things for planning, and combined with your kind of sim to real skills, then some teleoperation to guide the specify the tasks. So that's probably a good recipe to go in the future.
That's awesome. Yeah, because I mean, Chris and I, we've been very curious about like just different, I guess, like I mean, especially
Yeah.
humanoid, but like a different way, different data sources. Yeah, I mean, I do think that maybe beyond certain point, it's when the UX gets so good that maybe it's just enjoyable to do this. Like, but actually, you don't learn much from like a human teleoperating anymore. It's more just for the humans. Maybe it's an interesting experience for the human to teleoperate a robot at some point. But you actually don't learn all that much. Maybe you should just throw a world model or some kind of simulation, and you actually get and then through a VLM, you can actually do the whole thing.
Yes, yes, I think that's possible. So that's why teleoperation itself is so expensive. You shouldn't expect you can get like a huge amount of teleoperation data in the end, right? So word model or video learning, yeah, those are good things to specify, or at least. But for teleoperation, we do find in practice teleoperation itself usually serves as like a role to align or to kind of specifying users' needs. All those type of things is sometimes not easy to just use a language to specify the user's needs. Then in that specific cases, especially maybe for the robots is interacting with humans, right? Some of the very nuanced behavior, it's not just easily described through language, or we do have a lot of videos for those situations. So in this case, some teleoperation is helpful to kind of activate the capability of this kind of basic skills of the robots. Yeah, but myself is not like a big fan of like a huge amount of teleoperation either. I'm actually like I'm a good believer of simulation and sim to real. So I've been working on using synthetic data for kind of boosting humanoid robots and also robot skill learning for a long time. So that will continue being my main mission. And teleoperation, it's useful. So with this kind of simulation thing being developed, we can now also support teleoperation. So this is saying simulation is critical because without simulation, you don't even have a way to do teleoperation for humanoid robots.
Yeah. Okay. Cool. Chris, do you have more question about the paper?
No,
Yeah.
nothing
So
particular.
I
Very cool
guess
stuff. Yeah.
yeah, maybe as a wrap up, we usually like to ask this question like is are there any like other papers you come across recently that you want to give a shout out to that it doesn't have to be humanoid, right? But could be anything that kind of really piqued your interest you want to give a shout out to.
Yeah, I normally kind of like, I see a lot of like papers in this kind of like a humanoid branch and also for general robot learning. And recently I see one work from MIT studying kind of large behavior model. That's on my reading list, which I think is pretty kind of interesting. I will, my personally,
Russ, right? I think.
yeah, from Russ. Yeah, I will read that paper carefully. I'm not sure whether you can have like an episode discussing that paper. That would be super cool. Yeah.
Okay, we try our best get him on the pod. Yeah, I haven't read the paper yet, but I saw his he gave a recent talk at Stanford. That was really cool.
Yeah.
That was really cool.
Cool. Yeah. Awesome. Cool.
All right.
Well, yeah. All right. I mean, thanks so much for making the time, Lee. Really, really cool work. And I mean, thanks for open sourcing, I think, Open WBT, and glad to hear that you guys, sounds like you guys will keep on adding more primitive and make it even more useful.
Yes.
Yeah, I think it will help a lot.
Yeah.
Okay, cool.
Thank
Yeah.
you.
So I guess, yeah, thank you so much. All right, Chris, what have you learned?
Cool. Yeah, I thought this is a really interesting paper on how to do teleoperation by training these different skills. And I thought particularly I thought it was really interesting to hear about how he managed to use, or how they managed to use the like this balancing between RL, or between imitation learning and reinforcement learning, to get like these nice, smooth, safe transitions between all these different capabilities. And it seems like a nice, robust, scalable way to train whole body control policies for complicated robots. What did you think?
Yeah, I mean, I think when I saw the demo, I was like, okay, wow, like,
Yeah.
I mean, we've seen a lot of very cool demo, but I think in this particular case, I think it has a lot of use case for much more powerful way to teleoperate. I think,
Yeah.
because a human have so many degree of freedom. It is still a big, I think, research question, let's say, of what is the right way to do teleoperation that it is not too frustrating for the human teleoperator,
Yeah.
yet hopefully use all the capabilities across all these degrees of freedom that you actually have, right? So it's basically a question of whole body manipulation, right? Or locomotion. And so I think what he's doing here is a very usable stack. It's a very usable stack. Like for example, like what the folks in Stanford is doing with let's say twist, right? It's the full body motion thing, right? Like mocap, right? So obviously way harder,
That's
way
hard.
more frustrating for the
Very hard to set up. Yeah.
Whereas in his case, probably just put on some VR goggles and then the two controller, and then you get quite a lot of range. I mean, you can do the squatting down, you can do reaching out, and then he kind of have this skill ensembling side of it that take care of a few of these core skill sets. And, like he mentioned, there could be many primitive skill, but I think the three that he picked as a start is a very sensible combo.
Yeah, it's a good.
It already unlocks so many things that you can do,
Yeah,
right?
especially
like
since it's not just each of those individually; it's the combination of them because of the RL training, right? So, yeah, it seems like a very nice way to start to me. Yeah,
and I think it's. I mean, again, as a layman, I'm just trying to think like the difficult part is you can train up all this like individual, let's say primitive skill, but you need a model to figure out the transition. Let's say you're transitioning from moving to picking up, right? Like what is the right way to do it, right? Without breaking apart the robot, right? And he's mentioned something. It's not just transition, right? It's also like actually imagine when you're moving the robot while carrying stuff, like the center of mass would have changed, and so it's usually a combination of these skills that actually make the humanoid do a lot more possible tasks. So you definitely need something like this. Certainly, if you want to use teleop to gather more useful data as well. So I think this is it's great that they're open sourcing everything. But I think it's also quite curious what he was talking about, like beyond teleoperation, like the other modality, like synthetic. It sounds like he's doing a lot of work there. I don't think he didn't mention world model, so but he probably doing simulation, right?
Yeah.
But still, those are very much needed, I think.
Yeah,
So I
Data-driven
think I feel that
simulation
it's
and
kind of like a
everything.
common theme. It's like ultimately all these different sources of data, they all have their own trade-offs. So you should just gather whatever you can and then do co-training
Yeah,
eventually.
that
Don't
seems
waste.
like what everybody's doing, right? It's everybody's doing all of the above. That's the right way to go. It seems right.
Yeah, plug
Yeah,
some. It's
yeah,
things are never as
yeah. I
straightforward.
agree.
And it's like
Yeah,
video data. Oh, sounds great, right? But to his point,
right.
even though you can script the entire YouTube, like probably you're gonna throw up the other
Yeah,
99.9999%.
right.
You know,
Exactly.
so you
Yeah,
might as well just like collect your own video in the lab, right? Maybe to
that's what
I mean,
everybody's
however
doing.
you yeah,
Yeah,
I mean,
yeah. I
so
agree.
but I think in this particular work, it is really helpful because like I feel that for the last 1 year, especially since G1 come about, what we lack is really good teleoperation UX for you to fully leverage. Otherwise, like if you're just doing tabletop kind of manipulation, then might as well just use a mobile manipulator, right? Those mobile based, like with a mobile base. But if you really want a two-legged thing, you want to be able to squat down, right? To fully take advantage of the full motion that is, that you can get from a humanoid. So I think this is quite a big unlock, actually, something like this. So yeah, okay. Anyway, so that's my thought. Yeah, I guess we'll talk again really soon for the next paper.
Sounds good. See you soon. Bye.
All right, see you soon.